All right, for those that are online, can you hear and see? The screen is blank behind me for right now, but can you hear and see me okay? Anyone? Thank you. Okay. I wanted to backtrack a tiny bit and go and clarify some things with filtering. So with filters, size I want. So looking at this Bodhi plot, do a different color. Okay, if this is 0 dB, and we have something that looks like this, that didn't draw very well. Let me try that again. Okay, that looks better. Okay. First question is this, what kind of a filter is this? If you guys want to just put in the chat your thoughts on what filter this is. Okay, so okay, so most of you are putting bandpass. So a bandpass, and this is what I wanted to clarify, actually would look like this. So a bandpass has below 0 dB, or so it goes below 0 dB up to either 0 dB or above 0 dB. So what is the difference between a low pass filter and bandpass? So this is actually a low pass. So this is actually a low pass filter with a high Q. So it is not a bandpass. This one is a bandpass. And the way you can tell the difference between a bandpass and low pass is that a low pass actually will have at or above 0 dB, and so color, this portion of it is what is signifying that this is a low pass. So the value before it actually peaks is what is going to determine whether it's a low pass or a band pass. So for band pass, it will be below 0 dB. So that seemed to be a little bit of a confusion about filters that I wanted to clarify. So to identify if it is a low pass or a band pass, the differences between them is going to be that portion that is before omega naught. So this would be omega naught. This also is probably a high Q. And remember, with low pass filters, you don't want a high Q. So this is kind of not a non-ideal low pass filter. But the way you again can find it, is it low pass or band pass, is that beginning portion, whether it's 0 dB or above 0 dB. And a band pass will be below 0 dB. Does that make sense? Okay. All right, we're gonna try things a little different today. So on this, this is called a Menti. So you can either, it's hard to see this. You can either go to menti.com and type in this code. Try and make it bigger. Or you can use, yeah, you can see that now. Or you can use the QR code, and you're going to solve this circuit first and then put in there the value for RL and just put RL equals and the number, and then once you find the power, put in P equals. So you want to choose this load ZL so that the power dissipated in it is a maximum, and then determine how much power that will be. So go ahead and work on this, and then once you solve for those, you can put them in the chat or in the Menti, and we'll try this. Hi, are you joining?
Oh, I'll be on.
Okay, bye.
Alright.
So this doesn't seem to have worked in this one. Sorry. Let's see. I'm gonna try this one instead. This will work. Okay, this one will let you type special characters where the other one did not. So that is the number and that is the QR code for it. Alright, so finding RL and power. Alright, hopefully you can see from this that to find ZL, you're going to remove the load, and from there do A to B. And note that these are all the same node, but that this goes, splits here, and then it splits on this side. So A side is going to be separate, so it's going to be RTH is 6J in parallel with 8, and then you need to add the 4 in parallel with minus 5J. And so you can put that in Wolfram, or you can do it by hand. So this would be 6J times 8 over 8 plus 6J plus 4 times minus 5J over 4 minus 5J. And then you can multiply the bottom by the complex conjugate to get rid of the bottom. And this will give you eight 6J times 8 minus 8 6J times a minus 6J. And then this becomes 8 squared, and then the pluses and the minuses will cancel out, and then you end up with plus 6J squared. And you should still end up with the same after you add all these, 5.32 plus 1.89J. And then to find RL will be the complex conjugate. And so this is going to be 5.32 minus a 1.89 or 1.9J. So that will be your RL value. For power, we need to find V. And so from that, we're going to put VTH is between these two nodes. So we need to kind of find V1 and V2. So V1 is found from V1 minus Vs over 6J plus V1 over 8. I'm gonna put my ground here. And then for the V2 side, over 4, and then V2 over minus 5J. And then VTH is going to equal V1 minus V2. And solving that, these. End up with solve for V1 and then solve for V2, and then plugging those in, you get 0.31. At 59.5 was what that ends up being. So you just use the 0.3123, and again you could use Wolfram to solve for these, and then you end up with 2.29 milliwatts. All right. I'm not going to ask you to solve for the transfer functions, but this is a good practice to solve for the max power or even the Fourier to solve a circuit like this. So we're going to go through the steps of solving for V out over V in, which is VI. And then we want to actually graph that in MATLAB and see what kind of a filter it is. So we're going to use the node, the top node, as our Vx. And so our equation will look like, I'm going to do this current, so Vx minus Vi over R plus L was given as 1 micro, so 1 micro S. And then C is 1 micro also, so 1 over 1 micro S, and then this one is 1 micro S. So Vx is then going to be over 1 over, so I can just multiply it, and then this Vx will be 1 over that equals 0. Note that Vx is equal to Vo. So I don't know what Vi is here, so the only difference between solving this as a transfer function versus just solving this is typically we usually know what Vi is. So with the transfer function, you just leave Vi as kind of a known value, and then you're going to divide it at the end. So getting common denominators for Vx, R was 10, so this is 1 over 10 plus 1 over micro S. And then you bring the Vi over to the other side as a known kind of value. And then we're going to multiply this whole thing. And then we can divide, so this becomes 1, and then you divide by Vi. And this is our transfer function. So we take this quantity, or this portion of it, and we can type that into MATLAB. So I already did this, so this looks like So remember in MATLAB, you first have to define a transfer function variable. So S equals TF of S, and then I just put in the values for R, L, and C. And then my transfer function, I simplified it, but you could even just type it in as this. You don't need to simplify it more. And then you just do Bode mag. That will just plot the magnitude portion of the Bode plot. There's a phase portion too. And that ends up giving me this. So again, remember that you're looking at the before and the after of where it peaks to see, is this a low pass or a high pass? So same thing, let me go back to that. For this one, remember you're looking at it being at or above 0 dB is the clue that it is a low pass. But you can also do the same thing on the high pass side. So on the high pass, you're going to look for also, so for a high pass, it's going to look something like this, where it will be below 0 dB, and then it could peak, but then it's going to be at or above after it. So at or above 0 dB will define if it is a high pass. So again, we're going to look at where, before it and after the peak, is it above or below the 0 dB? So looking at this one, we can see that it just barely gets to 0 dB here. And so this would be, oh my goodness. I am sorry. You guys, I've been on mute for a while. Okay, going back to this. Okay, we go back to this one. So, remember on the filter that I went through, so you're determining if it's a bandpass or a low pass filter based on if you're looking at the 0 dB level of it before or after for high pass. So on a low pass, you have that 0 dB, it's above 0 dB or at 0 dB. And then for the band pass, you can see how it goes, it's below 0 dB before the peak and after the peak. So that is what's going to determine when it's band pass, is that before and after. If after it stays at or above 0 dB, it's going to be still a high pass. So on this one, we're looking at the difference. Oh, I was muted for this. So to plot this, again, you want to define the transfer function S equals TF of S. And then you can just plug in, I simplified that H2 equation, but you can just plug in this equation. Just make sure you have the parentheses in the right places. You usually want to not suppress the output, so don't put a semicolon at the end, just so you can make sure that it does look the same as this equation. And then you just type Bode mag. And then on this one, you can see that that peak is at 0 dB. So everything is below the 0 dB. So this would be a what filter? You guys can type it or say it. Anyone? I will, nobody's responding. So band pass. And that is because it's below 0 dB again on both sides of that peak. And the Q point of this looks like it's at about 10 raised to the 6, which will be 10, and then 5 more ones. So 6 zeros, 1, 2, 3, 4, 5, 6, and so that's going to be at 1 meg. 1, 2, 3, 4, 5, 6, yeah. So at 1 mega radians per second, that would be my omega naught. And then you look at if this is a high or low Q by going down by minus 3 dB from the peak, which would be at 0. So this is going to be minus 3 dB. So you can see here that this is pretty narrow. So this would be a high Q. So remember, this minus 3 dB comes from the 1 over the square root of 2 times whatever peak magnitude it is. And that value is 3 dB once that 1 over square root of 2 volt per volts is converted. And again, that's your RMS value. So that's why we use that value there. All right, any questions about these? So we did a max power transfer, and then we did this filter question. The last type of question is going to be the Fourier transform. So we will complete this on next Wednesday. Monday is another recorded video. Again, I'm also available for office hours after class right now. And so if you want to hop on my Zoom link, I sent that in the announcement as far as which link that is, or which Zoom ID that is. And I will see any of you that would want to come to office hours. I can answer more questions, but I have a few minutes if anybody has any questions here. Okay, I will see you guys on Wednesday in person, and we'll be back to normal at that point.